Hi everybody, in this video we will be learning about B-trees. Firstly, why the B-trees came into existence. So first, as the size of your data increases, even the index file size grows. As the index file grows, it becomes difficult in order to bring the complete index file into your primary memory in order to do any operation. So as a solution, tree structures were used in order to provide indexes to the large files. So what was done was the indexes was divided into smaller records so that we were able to fit the index files into the memory. So the two structures which we see is binary search tree and AVL tree. Binary search trees and AVL trees have a tendency to grow to multiple levels as the number of keys increases. So there were a few problems or flaws when it came to your binary search trees and AVL trees. So as you know, binary search trees and AVL trees are built downward from top. So the first element inserted will become the root node. Next you are going to do the insertion either to the left or to the right. So you are starting from the top and building it downwards. So that is what is called as top-down approach. So as an alternative, another solution called as B-trees was considered, wherein the tree was built from bottom and it was moved up, that is bottom up approach was used here. B-tree is a multi-level indexing. It provides an index for an index. That is, as your index file is divided into smaller records, so the leaf level will contain the index records. The upper levels will be the index to this particular index. So that is why it is called as multi-level indexing. You are providing an index to your actual index file in order to make it faster to access your data. Let us see a node structure for your B-tree. Each B-tree contains a order. Order indicates the number of elements a B-tree node can hold. Unlike your BST and your AVL trees, B-tree nodes can hold multiple keys. That is, if the order is 4, you can store 4 keys into your node, and along with 4 data fields you will have link fields. These link fields are used to link to the next level or the child nodes. So let us see the construction of your B-tree for a given set of input. So let us say these are the set of keys which I want to insert. So first of all, the data in your index should always be in a sorted order. So starting with C, since your node is initially empty, C is inserted in the first place. Next, when you insert S, since S is greater than C, it is inserted to the right of C. Next element is D. D is greater than C, but D is less than S. So it should be inserted in between C and S. So what we will do is we will shift S to the next location and insert D in this particular location, which will result in this particular structure. Next element is T. T is greater than C. T is greater than D. T is greater than S. So you are inserting it into the last position. So we will get this particular structure. Now next element is A. When you try to insert A is smaller than all of these elements. So it should be inserted in the beginning. But as you can see, your node is full. So you will have to do a split operation in order to accommodate your data. So we will see the split operation. So first of all, when you split, we are going to divide this particular node into this structure. 3 elements will be taken into one node and the other 2 elements will be taken into another node. So we will get something like this. So ACD in one node, ST in another node. Now since this is not a complete tree, we need to build a parent for this. A parent in your B-tree structure will have the largest elements in the child nodes. Since the largest element in the child nodes are D and T, the parent will contain D and T like this. So whatever is smaller than D will be towards the left, and whatever is greater than D and less than T will be in between this. So this is how your B-tree will be handling overflows. Whenever a particular index record overflows, you are going to do a split operation and create 2 nodes. So after that you can continue the insertion. First thing to note is all the insertions will happen in the leaf level. So all these keys what you see will be there in the leaf level. The higher levels are just an index to this particular final leaf level. So what we have is a next element, what we have is M. So M, so you are just going to do the comparison starting from the root. M is greater than D, M is less than T. So you are going to insert in to this particular node. So when you are doing the insertion in this node, you are going to compare where the element M should be inserted. So M is smaller than S, so it should be inserted in the beginning. So you will get it as M, S and T. Same way, when you are done with M, you are going to go for the next element P. Again the comparison starts from the root. So you have P is greater than D, but P is less than T. So always start the comparison from the root node and then find the node where you have to do the insertion. That will be always to the leaf level. In the leaf level, you have to insert the element in the proper position so that the elements in the node will be in a sorted order. Since you had inserted P, your data would have been M, S and T. Now when you insert P, P is greater than M and so it is less than S, so it will be inserted like this. So we will get a structure like this. You can see ACD, the first node is as it is. The second node contains now M, P, S and T. Now next element to be inserted is I. Now again start the comparison at the root. Always you have to start the comparison at the root. So I is greater than D, I is less than T. That indicates that you need to insert it to this particular node. When I try to insert I again, what happens here is it overflows. Since you overflow, you are going to do a split operation again. So you are going to take these three elements into one node, the other two elements into another node. So you will get IMP in one node, ST to another node. So let us see. So this will be the structure. Now as you know, the parent should contain the largest elements of the child nodes. So that's why you have D, P and T into the parent node. Now I is done. So next element is B. Now B is less than D, so it should be inserted to this particular node. Since B is greater than A and less than C, so it should be inserted in this position. Again D will be shifted here, C will be shifted here in order to make space. Then you are going to insert B. Same way next element is W. Now when you look at W, W is actually greater than D, W is greater than P and W is greater than T. As you know, we are doing an insertion only to the leaf level. Since it is greater than T, it should be inserted towards the right, but there is no node to the right. So what we will do is, we are going to insert it into the previous child node, that is this node. In this, when you insert W, here what we will get is the highest value which was previously T, now it has changed to W. This W needs to be promoted to the parent node. So this is called as promoting. So when you insert W, let us see what will be the structure. W was inserted. So in the parent level, W was upgraded. So after W is the value N. Since N is greater than D, N is less than P. So it will be inserted in between this. So it comes to this particular child node. So previously we had I, M and P. Now N will be inserted in between because N comes after M. Next value is G. G is greater than D, so you are comparing towards right. Again G is less than P, so it will come to this particular node again. So when you try to insert, again there is going to be a split operation. So it will divide it as GIM in one node, NP into another node. So you got this particular structure. Again the largest elements in each of your child nodes will be promoted to your parent. So you have D, M, P and W. So D, M, P and W will be the elements of your parent node. So you are done with G. Next element is U. So U is greater than D. So U is greater than M. U is greater than P, but it is less than W. So you are going to insert it into this particular node. So what happens here? it is greater than S, greater than T, but less than W. Sorry, it is less than W. So you are going to insert U to this particular location. So you have S, T, U and W. Same way when you insert R, so what happens here? So when you try to insert R, so R is greater than T, R is greater than M, R is greater than P, but R is less than W. So again this will be inserted here itself. Now previously we had S, T, U and W. When you try to insert R, it is again overflow. So you are going to do a split operation wherein it is divided as RST in one node, U and W into another node, which will result in this particular structure. Now, so coming to your parent, previously in your parent you had D, M, P and W. So I will write it here. Now as you can see, there are 5 child nodes now. So since there are 5 child nodes, we will get D, M, P, T and W now. Since again your parent node has been overflown, you have to again do a split operation. For this again you are doing the same thing which you did with the leaf nodes, DMP to one node, TW to another node. So that is what we are doing here. DMP comes to one, TW becomes another node. Now you are linking with the child nodes. If you have 3 elements in the parent, obviously it will have 3 child nodes. So 3 links will be given. TW there are 2 nodes, so 2 child nodes will be given. So like this you are going to do a operation here when you are doing a split to parent. Now again as you can see, this is not a complete tree, it needs to have a root node. So to create your root node, you are going to take the largest elements in the child nodes here. So you have P and W, which will be promoted to the next level, that will become the parent. So this is how you are doing a construction of your B-tree structure. So as you can see, after the insertion of all the elements, it will still be in 3 levels. I hope you can complete this tree structure and try it on your own. Thank you.